All right, today we're going to take a look at exponential modeling with percent growth and decay. So here we've been talking about exponential functions and graphing exponential functions. So now we're going to get more into the application area of exponential functions. Okay, so if your exponential function has a growth value of greater than 1, then it's increasing or it's exponential growth. If your exponential equation has a growth factor between 0 and 1, it will be decreasing when you graph it, and then that will give you exponential decay. So first we're going to use an example about a savings account. So if you deposit $400 into the account, you are receiving 5% interest, then how much money will you have? And how can you calculate that from one year to the next? Okay, so this kind of takes us step by step through that process. All right, so how much will a savings account increase by over the course of a year? Well, if you start with $400 and you're going to earn 5% interest, okay, or writing that as a decimal, be 0.05, multiply that, and you're going to earn $20 in interest. So at the end of the year, you're going to have the $400 that you started with plus the $20 that you earned in interest. So you will now have $420 total. Okay, so by what single number could you have multiplied the 400 by in order to calculate your answer in part B? Well, the 0.05 that I used is just for the interest. So if I want everything, I would actually want to multiply by 105%. So the 100% gives you back the original $400 that you invested, and then the 5% gives you that increase of the $20. So written as a decimal, that would be 1.05. So your growth factor is 1.05. It's greater than 1, so we're going to be increasing, and this will give you $420. So using that concept, then how would you determine how much money is in the account after 2 years? So using that same idea, so after 1 year, you'd have 1.05 or 105%. So then the second year would be the same thing. So the 1 represents that 100%, everything that I had in there previously, and then the 0.05 for the next amount of interest. Okay, so another way you could write this would be 400 times 1.05 squared, okay, because you're leaving it in for 2 years. Okay, so for 2 years, that's going to give you $441. So then for 10 years, you would do the same thing, except it will be to the 10th power, and after 10 years, $651.56. Okay, you will want to make sure that you know how to do this on your calculator. So as I'm making these calculations, you need to be doing them on your calculator also, so that you know that you are inputting your information correctly. Okay, part E, give an equation for the amount in the savings account, S of T, as a function of the number of years since $400 was invested. So that's that same concept we just used in part D. We're just going to formalize it into an equation. So many times you will see T used when you are working with compound, exponential growth and exponential decay models. Many times T will stand for years, but depending on your situation, it could be days, weeks, hours, minutes. Okay, and then using the table on your calculator, determine to the nearest year how long it will take for the initial investment of $400 to double. Okay, so what we want is, if we want it to double, we are looking for $800. Okay, so if you pull up your calculator, then go to your y equals and type in your equation. So 400 times 1.05, and then we're going to use x as our variable instead of t. But what you can do is I can graph it, of course, but what I really want is the table. So here the table is on the graph button. You can see it in blue. So you're going to do second table. And if you look here at 0 years, we start with $400. After 1 year, there's that $420 we calculated. 2 years, $441 that we also calculated. Down here at 10, there's the $651.56. Okay, now, since we want to know when it's going to double, we want to know, when does it get to $800? Well, right here at 14 years, you're at $791, and then 15 years, you're at $831. So it's going to be just a little bit after that 14th year, then you will have $800. So 14 years gives you $791.97. So when will it double? Well, it's actually going to double after that, in that 15th year. Okay, so let's go back here. Here is an exponential model for this situation. The variables have changed, but it's still that same concept. So you can see the 1 plus p, so that was like that 105%. So the 1 for the original amount that we have, and the 0.05 would be the p, would be the amount of increase. Okay, so example or exercise 2, which of the following represents this situation? So savings account $250 was invested at an interest rate of 3% per year. So on that one, it's going to be number 2. So $250 is what I originally invested. Since I'm getting 3% each year, then 1.03 is going to be that growth factor, and then to the t power. Okay, so it's going to be option number 2. Okay, now besides increasing, like we were doing with a savings account, you can also decrease. So instead of adding that 5%, if we're losing 5%, we would subtract it. Okay, so here we're just going to practice rewriting what the growth factor would be in the cases that you are decreasing a quantity. Okay, so 10%. So if you decrease by 10%, well, you no longer have 100% then. If I decrease by 10%, I now have 90%. Or as a growth factor, you can think of it as 1 minus, okay, as in decimal form, 100% minus 10% would give you 0.90. So there's your growth factor. It is decreasing by 10%. B, if you decrease by 2%, same concept. So 100% minus 2%, well, that's going to be 98%. So again, as a growth factor, think of it as 1 minus 0.02, or it'd be 0.98. So your growth factor is 0.98. Again, it's going to be decreasing by a little bit each term. C, 25%. Okay, same concept. So 100% minus 25, and that gives you 75%, or 1 minus 0.25 is 0.75. Okay, D, you are only decreasing by 0.5%. So 100% minus 0.5% is going to be 99.5%. Okay, so as decimal, 1 minus, now move your decimal 2 places to the left. So that 0.5% is going to be 1 or 0.005. Okay, move it 2 places to the left, and that will give you 0.995 as your growth factor. Okay, so again, you can either increase where you would be adding a percentage, or if you are decreasing, you are subtracting that percentage. Okay, same thing here, a decreasing exponential model. It's the exact same thing as what we saw previously. It's just that you are subtracting a portion instead of adding on a portion. So here's an example to represent that. If the population of a town is decreasing by 4% per year, and they started with 12,500 residents, which of the following is its projected population in 10 years? All right, so we're going to need to set up an equation, calculate for 10 years, and then we can find our correct population. Okay, so kind of going back to this y equals a times b to the x. Okay, that's that form of what you just saw here. Now, if we're going to use this material's notation, okay, it'd be q sub o times 1 minus p to the t power. Okay, again, the a and the q sub 0 are representing the same concept. That's your initial value. Okay, so that's your initial value, how much you start with. Okay, here the b is our growth factor, and in this equation, that 1 minus p is representing the growth factor. Okay, so same concept, just a little different way to write it. And then x and t, that's your time allotment. Okay, so for this one, we are starting with 12,500 people. You are decreasing by 4%, so that's going to be 1 minus 0.04 to the t power. So 1 minus 0.04, okay, or minus 4%, that's 96%, or 0.96. And then my time is I want to know in 10 years what my population is going to be. And it's going to be 8,310 approximately. Okay, so it's going to be option number 4. Again, try that in your calculator. Make sure that you can calculate that correctly. Okay, and that is going to be it for this lesson.